Alright, so we're gonna try to get a little code snippet to work, because we tried to get it to work yesterday, but okay, so anyway, like the whole thing we're trying to accomplish here is this. So, what is supposed to happen at my AI buddy, which may or may not work? Yeah, so just to try to understand what's supposed to happen. These are so we're looking at four-dimensional boolean function. So we have like 16 inputs. The rows correspond to inputs, and then the columns are like the 4 choose k like subcube addresses. So the first column is like 4 choose 0, which means there's 1, and it's the entire subcube. It's not really a subcube, it's the cube. And then the next 4 columns are 4 choose 1, which means like you're picking a single coordinate, and then you're looking at the 3-dimensional subcube if that coordinate is fixed to a 1, and then the other one is if that coordinate is fixed to a -1. And so the different, so like purple is one of those subcubes, and blue is the other one. And then we have 4 choose 2, which is 6 2-dimensional subcubes, and those are subcube addresses. So anyway, like the colors only make sense within a single column. So like this yellow, like these 4 points are all in one subcube, like literally a 2-dimensional face on the 4-dimensional hypercube. But that is a different subcube than like the yellows in a different column. And what we're trying to do is we're trying to visualize nonlinearity structure, which is what these highlights are supposed to do, although they don't currently. I think there might be a simple fix, which is I'm just going to flip the X and Y. Otherwise, it's going to be like a long, arduous debugging process, which will make for some pretty good content, I have to say. But what we're trying to visualize is if you fix a function, particularly like a nonlinear function, we want to go through all of the subcubes and highlight like the nonlinearities. Which so the idea is that like the red would be like you'd highlight both elements of a pair of inputs that are negations to each other if the function assigns both of those points the same value, and there's another pair within that subcube that the function assigns a different value. That makes like perfect sense and everything. So anyway, we're just gonna, like, it doesn't work right now. So we're gonna see if all I have to do is flip the X and Y coordinates. Yeah, which I think is right here. We'll just see if that works. But I think first of all I need to, I don't know if I guess I am connected, okay. So I need to pick a random function with this code that picks a random function and also does a bunch of other stuff. And then Yeah. And then this code, which is the code we're trying to fix, it breaks immediately. Ooh, right. Yeah. So, this is the function. These are subcubes where you have a nonlinearity. So this is saying that like input 3 and input, no. This is saying that like 3 and 5. Oh, I see. Okay, on this subcube. Yeah, so we're trying to visualize. 3 and 5 are negation pairs on that subcube. Meaning, if you just look at the, if you ignore the subcube address bits, right? Yeah, so 3 and 5 are being assigned one color, which is -1, and then 1 and 7 are negation pairs that are being assigned a different color. Okay, so that's working, and yeah, then basically we're just trying to plot this information on the visualization, and yeah, so yeah, this is going to be like a long, arduous debugging process. Been a lot of fun. I am going to well, okay, let me get another function that doesn't give me that 000 bug. Good. This is like a different function. And okay, see if we get the same bug. Okay, we don't get any bugs. Yeah, so it's not. Okay, so now I'm just gonna try if you can flip the x and y. Yeah, is that gonna magically work? No. Great. Good stuff. Yeah. Okay. Oh my god. Alright, so here, okay. Right, we have a little code snippet that produces this. And again, what this is doing is it's just analyzing this function. And it's looking at all of the subcubes, and then it's printing if there's a nonlinearity present on that subcube. And then also what's supposed to happen is that these subcubes, like this is a subcube, correspond, let me not print that, they correspond to columns. And yeah, let me get rid of this one. Where is the other, oh yeah, okay. Let me get rid of that. Nice. Very nice. So, also this is like GPT code, which is why I gave it a weird title. Just gonna, we don't need a title because we're like really cool. We're like really cool dudes, and we don't need titles. We don't need labels. Okay. So here's the whole difficulty. Like, this column is this. This column is 0, 0, 0, 0. And, yeah. No. Yeah. Right. No, there's very serious bugs happening. Okay. So one problem is this, which is where I produce the subcubes and it's conflicting with x, which is also the inputs. And yeah, I don't want that. So I think this needs to have a different name. But then, like, I don't even know logically what this one is supposed to be. Right, this one is supposed to be S. Okay. Alright, so we'll say like we were conflicting with the capital X because it's just supposed to be the inputs. Okay, so this produces all the linear threshold functions for n equals 4. Specifically if they're balanced. And is this sorting them in some way? No, I think it's lexical order. Okay, then we pick a random function and then we do a bunch of visualizations that we're not focusing on presently. But yeah, this is our random function here, and then the code we're trying to, that does produce cool visualizations. Yeah, I mean all of these are the linear threshold functions, like, I think that this is where they disagree with this function. Right. One, because, like, the first column here, these are all -1. So 1, 1, 1, so like the first 3 will disagree. And then, yeah, and that's what's happening. So the purples are bit flips of each LTF in order, or like in lexical order, with respect to the random function. And then these are if you sort the LTFs by the Hamming distance. And these are the LTFs themselves, sorted by the Hamming distance. Anyway, yeah, like, none of that matters. We're not doing that. Okay, so let's see if right. Good. Yes. Okay, so right. Okay, so we're using different subcube representation. Because this, right, that's using 0s and 1s just to indicate whether a bit is selected. Yeah, like the selected bits correspond to columns in some way that I don't understand. That's kind of the, right, I mean, like, this column is all 0s. You know, this one is like 0, 0, 0, 1, and so forth. let's see, what do we got going on here? Holy shit, dude. Selected bits. Yeah. MRC equals des. Dang, man. It's like it's a simple thing, but like it's very complicated. It's alright, we're just gonna start it for 6 hours and then subcube address. Right here, the subcube addresses have okay, so there's a difference between the column and the actual address. Yeah, that's okay, that's kind of some of the right. So what's happening here? Right, these are binary vectors, and it's a 1, indicating if that coordinate participates in the address, like it's a fixed coordinate. Whereas up here, the subcube address actually gives you the address, and it has a 0, and like the free coordinates for that subcube. And so yeah, I think so it's kind of like selected bits. I think that's fine. I mean, yeah, this code is producing the actual like colors, and that looks correct. So it's just the problem is, yeah, I mean, we need to go through, I mean, what we could do is just go through this, and yeah, that's the problem. Right. So I mean, like, the column for this subcube address, like, first of all, we ignore this 1 because that's a bias, so we're ignoring that. And so this, this, like, the selected bits here, like this would correspond to 0, 0, 1, 1. And the problem is that we don't know what column that is. But that is being determined up here. We need like a function that maps this vector to a column. Yeah. 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 So I think it's like we just have to figure out, we have to drop the last index, the last element, and then, take the absolute value to convert it into selected bits, and then we can just make a selected bits to column map. Which is like right here. So yeah. Yeah. Okay. Selected bits to column. And then, I mean, there's probably some mathematical way of doing it, but I don't really know what the mathematical thing is doing. Like C is the column. So you literally just, also I don't think I need this. Or, I mean, I think I can just directly call this selected bits. What doesn't matter, okay. But anyways, okay, so I'm just going to, also separate thing, say SB to call for tupleize the selected bits equals C, the column index. Very good. Very good. I mean, I'll just see what that does. Oh no. No, what's wrong? Oh, it's right here. Okay. Ooh. That's not what it's supposed to do. That was weird. Oh, oh, yeah. What? Oh, I see. Wow. Okay, so it just needs to say subcube. Possibly. Yes. Good. Good. I don't know why it's throwing an error there. That's weird. But, yes. This is very good. Yeah, those are that's what we're going for. And, in Zine, yeah. I think, yeah. We can then loop over. Where am I printing this thingy? Print KV. Yeah. Okay, so I'm gonna pull that out. I mean, I don't know what any of that code does, but I just know that what I need is this. Like these are just the nonlinearities as opposed to like all of, yeah. So I think I can just iterate over nonlins and yeah. doesn't work. So non-items. Yeah, right. So I mean, like the K on that is gonna be this stuff, right? Yeah. So right. Okay. So we have to drop the last index and make the thing into an absolute value, and then look it up in the subcube 2 column to get our column. Yeah. Okay, so I'll get rid of that. And then, right. Okay, so then we need like K equals, I mean, tuple np absolute value np dot array K drop the last index, right? Yeah, and then C equals whatever I called that thingy, sp2 call. Yeah, sp2 call. Okay. Yeah, so like everything should work now, isn't it? What is D? We don't need that. We need V. This is V. Where am I making D? I should get rid of D. Is there a D anywhere? It doesn't matter. Okay. Holy. Oh my god. It works. It works. It works. Yeah. Now the color scheme. Yeah. Okay. So we'll spend a little bit of time analyzing that. I just need the color. I don't know where I'm making the color here. Hello. Where is the color? Oh, right here. Okay. CMap. I don't know, like, I don't know any of the, I think one is magma. Magma. Oh, whoa. That looks, is that better? Yeah, that's a little better. Okay. Alright, so now we will look at this. Yes. Okay. Right. Right. This is very cool. This is very cool. Okay, so like what's happening here is alright, a 4-dimensional boolean function. And okay, yeah. So like what this is saying is that the particular function assigns the same color to 2, which is, you know, like 0010, and also 13, which is 1101. Now, is that correct? Yes, because it's 8 plus 4 plus 1, you know. So anyway, apparently, well, okay, you know, let's just confirm that. If I can, I don't know where the okay, this is the function. I mean, the top are the indices, so you don't have to count. On the bottom is the actual function. So what this is saying is that 2 and 13 are assigned the same value. 1, 1. Oh man, that's very cool. But also 3 and 12 are assigned the same value, but the opposite value, which in this case is -1. Oh my god, I have a bug in the house. And -1. Right? And that's nonlinear. Like, you can't, yeah. Yeah. I have, like, bugs in the house. That's cool. Right, okay, so what this is saying is that that's nonlinear. And an implication of that is that if you flipped the output for any one of those 4 rows, it would eradicate the nonlinearity on that subcube. But there very well may be other nonlinearities happening. So for instance, like if we flipped this input 3, like, which in binary is 0011, you know? Right, I mean, like, you know, like we're visualizing like a boolean circuit, so all of the inputs are bits. Anyway, if we flipped the output assignment to that input, the you know, like, yeah, there wouldn't be a nonlinearity in this column. But for instance, if you look at this column, it wouldn't influence that column, and so there would still be a nonlinearity on that column. You know what? We can check that. Yes! We can totally check that. Okay. Yeah. Yeah, we can check that. So, yeah. Where is my function defined, though? That's the problem. Dang. I think I can just do it up here. So I'm just, because the function is defined, like, here. And we're getting, like, balanced functions. Yeah, I mean, this will make it unbalanced, but that's fine. So anyway, I'm just literally gonna say, which may or may not work, f3 equals, I don't know what it currently is actually, equals, okay, so we want to make it a 1. Oh, I could have just multiplied it by itself. No. I could have just multiplied it by -1. Yeah, we'll just do that. Okay, times equals -1 dot. Not sure you need the dot, but okay. So yeah, I don't think I'm gonna be using this, so I'll just get rid of that. Okay, so this is the original function. OG F, and this is if you flip that 1 bit. Oh, you know what? This is actually bad because when you run it again, it's gonna, yeah, you're gonna like get out of sync. That's fine. So, yeah, I should, you know, like, I should add the actual function as a column, but I'm not gonna do that this time. Right, right, look at this. Look at this. We have like a sweet animation. Look at that. That's amazing. Like it did what I said it would do. You know, like it got, like, there's no more nonlinearity on this column. That nonlinearity goes away. At the expense of, it produces a nonlinearity at the next column. Is that the only other thing that happens? Yes. Everything else is unchanged. That's crazy, man. That is crazy. Yeah. Yeah. That's cool. That's very cool. Yeah. Yeah. Let's see. Right. Like the main motivation for doing this was this concept of like sensitive inputs. Like what you can kind of see here. Like this is saying like if you flip this guy, it will get rid of the nonlinearity here. Yeah, okay, we're gonna flip that guy, but I got too fancy up here with the f3 multiplied by -1. That needs to be a direct assignment because otherwise everything gets out of sync. Okay, so we're just going to directly assign that to be a 1, I guess. Well, okay, let's go back to the original, actually. Let me check that this is the original. Yes. I mean, like I don't know, this is, you know, this is like the character encoding of the PNG or something. So those are the same. I feel like the probability of that happening, if they're not the same, would be pretty low, but I don't know. So anyway, yeah, that's what we want to do, is look at this guy, right? Because that, right, like if, okay, so like if you flip input 13, which is 1101, and we're just going to say the function, you know, assigns the opposite value. It's going to get rid of the nonlinearity on this row. It should get rid of the nonlinearity on this column. I should have said column over there. It should get rid of this nonlinearity. Should get rid of this nonlinearity. Yeah, it should fix every single one. You know, unless it doesn't. But if it does, that, you know, that kind of has the implication that this particular random function that we picked randomly, you know, is like one bit flip away, like, from being a linear function. Yeah. So, okay, let's flip that bit. 13. Good. So I have to see what 13 currently is. It's a 1. So we're going to make it a -1. F13 equals -1. Alright. Ride or die. Whoa! Holy sh... Okay, yeah, so my, my intuitions were correct. It's that function was one bit flip away from being linear. Okay, let's look at a different function. Yeah, I'll maybe look at 2 or 3 other functions, yeah. Okay, so anyway, this is like a function, apparently. And this, by the way, is saying that the closest linear functions are having distance 6. Which I think is going to imply that you're going to have to flip 3 rows? I don't know. We'll just see what happens. Oh, yeah, let me get rid of that part. Alright, so let's look at the original function. Whoa. This is very nonlinear. Yeah. Okay, so this function doesn't have the same, its nonlinearities are much more distributed than the other one. Like the other one, there was like a single row. Right. Like here's a conjecture. These highlighted cells, the count is constant. That's a very low confidence. No, that's almost definitely not true. But I mean, like, there seems to be, like, like on the other function, the nonlinearities were, like, concentrated on the lower dimensions. Okay, you know what I'm going to do is I'm going to copy-paste the random function code into the other cell, so that way we can just look at a bunch of functions. Yes, which may or may not work. Alright, bombs away. Just gonna open that guy. Let's do another one. Just gonna open that guy. I like do another one. Do that guy. Which by the way, these are all balanced random functions, meaning they have the same number of outputs that are 1 and -1. Okay, so oh man, it's a different zoom. It's a different zoom level. Okay. Right. Yes. Oh, okay. Now this one seems to have... Yeah. I mean, yeah, okay. So I think just by eyeball, that disproves the conjecture I made 20 seconds ago. Like, yeah. Anyway, yeah, that's a cool stream. That's a good stream for today. We'll just call it there. Please use a keyframe frequency of 4 seconds or less. Oh no. Anyway.